Welcome to my circuits lab. This is lab 4. I'll go over the overview, equations, models, a brief overview of lab results. So the purpose of this lab is to use the principles of energy conservation and current conservation to predict the behavior of the circuits containing resistors in a series in parallel, to use multimeters to measure the actual values of conventional current and potential differences in the circuit, and to examine the behavior of the ohmic resistors and capacitors. So the loop rule basically says that the sum of all electric potential differences around a loop is zero. So due to the circuit being a complete loop that we're working with, there is no potential difference. And the node rule is saying that the amount of current flowing into the junction is equal to the amount of current flowing out of the junction in a steady state. So the current is in is equal to the current out, and our I1 is equal to I2. So in our first model, I have in the top right-hand corner, you can see the circuit that resembles the one that we all did in the lab report. I made it with the FET circuit construction kit. I predicted that the ammeters at the top would both display 0.0204, and once I connected the second ammeter, my answer was confirmed. Here's an image. So basically, a brief overview of the lab results is the ammeters both display 0.02 amps. The ammeter does not have any resistance as the capacitor is charging. The current in the circuit decreases, and when the battery is removed from the circuit, the capacitor discharges and the current starts to move again, but slowly decreases. And the discharge time for a 10 ohms light bulb is approximately 16.682 seconds, and the discharge time for a 20 ohm light bulb is approximately 28.203 seconds. Here is the graph that shows the difference in potential. And so here is the 0.96 drop and then the 2.04 drop. And then here are those observations. I'll go over the key details. The ammeters both displayed 0.2. When it was backwards, it was the same. And the ammeter doesn't have a resistance. As the capacitor is charging, the circuit decreases and there's an exponential decrease. And then the discharge for the 10 ohm light bulb was the 16.68 seconds, and the discharge for the 20 ohm light bulb was approximately 20.23 seconds. Better images. Here's my work and the graph again. More work. This is showing that the capacitor is the resistor is being skipped, and that's because the current takes the path of least resistance, and so that is why when we calculated this, the ammeters don't have any resistance because it's actually just skipping that. That's why it's 0.06 amps. Here's my work for that. Here's an image of the capacitor. And the current through the first circuit is equal, so the current will take the last of least resistance, as I was talking to you about before. When a capacitor discharges, its rate of discharge decreases as time goes on, and when a capacitor charges, the rate of current decreases as time goes on. And then my computed value didn't match up, but I believe that is due to my personal error, but I had a negative 0.561. And the system is the circuit right here. The first circuit had two 1.5 volt batteries, and there is a 47 ohm resistor and a 100 ohm resistor. Second circuit had a 9 volt battery, and this light bulb was 10 ohms, 20 ohms, and 30 ohms during our test, and this was a 0.2 Faraday capacitor. On conclusion, similarities, differences, possible errors, what if, and some similarities were in the beginning, my calculations were spot on, and differences was in the end when I did that graph, I believe due to human error, of course, that it was incorrect. Possible errors, mistyped data, not correctly coded Excel sheet, not small enough times towards the end, therefore I got inaccurate data for our calculations. So what if I was doing the lab in real life, and how would this affect the ammeter? So if I was porting this form in this lab in person and not in the virtual simulator, the ammeter would most likely have some value of resistance. It might also give me inaccurate data if I measure incorrectly or if it was calibrated wrong. So in the simulator, there was absolutely no resistance with the ammeters, so that would be a difference. difference. And then if I was doing the lab in real life, how would the real capacitor or with no resistor in the circuit work, and then the batteries. So basically when I using a real battery, I might find issues like a loss of power, experiencing resistance in the wires as well as in the battery. Therefore, the time calculated in real life might be longer than time calculated in the simulator. And that is it. Thank you.